Uh, Good afternoon, everyone. Let's continue to discuss this paper, Knowledge Networks and Asset Pricing, the Invisible Supply Chain. This paper was done by Professor Shi, and so this is a very innovative paper because the author tried to count the patents and patent citation into the stock return premium. The topic sounds very technical. However, the intuition is very practical because traditional supply chain analysis usually focus on like a physical input, chips, battery, steel, components, and supply customer sales. It's tangible. But modern firms like Magnificent Seven compete not only with the machine and the physical goods, they also compete with knowledge, intangible assets, such as patents, patent citations, algorithm, software, data, design, and technical know-how. So modern firms rely on cheap software. All these are intangible assets compared to traditional supply chain focus on physical goods and tangible assets. So this paper actually asks one very important question: can this invisible knowledge supply chain become a systemic price in stock markets? So the paper's answers, I say, you read the paper, you see the answers was yes. But how do they design the paper? It's very smart. Why should you guys learn this and care about this? Relative to motivation and resonate is very important for the intangible assets, know-how, and knowledge, and not only machine, create firm value. So Magnificent Seven, okay, so this firm, NVIDIA, Apple, Google, Meta, Tesla, not really depends on materials or machine. They really heavily rely on chips, software, algorithm, patents, data design, and ecosystem. So traditional supply chain is different from the modern supply chain, which focus on knowledge and intelligence, property linkage, which can create systemic risk. So we have to price this risk into the model. We no longer need to ignore this. So for us, knowledge network help explain why some firms are strategically exposed to innovation shock, while some others not. So this is the network framework. Traditional physical input-output network. So auto sectors, the input was like a steel, chips, battery. But for modern supply chain model, we focus on knowledge input and output network. So like electronic vehicle, AI product, the input will be like a patents, algorithm, and battery chemistry. So this was input, this was output. And this create a network. And next slide, we will show you the interconnected network. So you can see that this is output, this is input. When the arrow comes to here, this is output. So this paper asks some general questions. However, there have 3 detailed questions too. Question number 1, does knowledge network sparsity predict consumption group? And question 2, do firms exposed knowledge network sparsity earn higher expected return? Because if this is a risk premium, investor will require higher return to compensate the risk. So this is the question number 2. And 3 is, does knowledge network risk help price the cross-section stock return? Whether this model can apply to cross-section dimension. So the paper's research questions is, the structure of a knowledge network really affect the aggregate consumption risk and the stock return. So there have 2 dependent variables. The first is consumption. The other is stock return. Okay, so this paper designed like this. Prior literature ignored the intangible assets, only focus on physical supply chain. So this paper act intangible supply chain, like knowledge, IP network, patent citation flow, knowledge sparsity factor into the model, and comes with the result, consumption growth, and stock return. We will go back to here to talk about the contribution of the paper. We will come back to here. But before going into the next stage, let me ask you, what is the key missing input in traditional production network asset pricing that this paper tried to add? It's a label, cost, physical materials, or 3, or D, or E. Multiple choice. This paper at what dimensions? Seven, 9, 10. Okay. We take a look at them. Okay, so yeah, knowledge, intangible assets is the key of the paper compared to physical materials, which has been counted in the model, in the traditional model. And this paper actually does not mention any labor cost so far. Okay, so we have 85% port for this answer. So let me briefly introduce the input-output network. For sector I, this is the input for physical input from other sectors. So I wrap with a blue line. So physical input to physical output through this sector I. So this is one inflow, outflow. And another is knowledge input, intangible, from the other sector into sector I read with red line. So knowledge input into sector I and produce another knowledge output to here. So for each sector, by input, physical or knowledge, produce goods, produce knowledge, could be physical, could be invisible, all become linked to the rest of the economic, and these form to ecosystem of the network, sector I. So for the provider, we call this sector J, and the user is sector I. So knowledge-based model, theta Ji means share of knowledge input from the provider, right? So this is a J, and into the user, which we call sector I. So sector J into input to user, sector I, and the share, we count this as a theta Ji. So share of knowledge input used by sector I from sector J. So this is a knowledge network share from two sector Ji. And another measurement which is important is physical. Relatively, supply is J, right? So this is the share of physical input, J, into I. The same logic, but we count another coefficient of the share is WJI. So if you see the theta Ji is the knowledge share, intangible. If you see the share is WJI, then this is tangible, physical input output. So if we have this relationship and we count along with the compute state customer sector data, we can know the inflow and outflow, input and output relationship to create the network. For example, one firm has 4 different types of knowledge input. Each count 25%, so equally weighted, right? So this is equally weighted from one sector, and the other sector is the input have highly rely on A, knowledge A, and less likely rely on B, C, and D. So if this is the input format, which one is low sparsity and which one is high sparsity? input heavily rely on and equally rely on age. This is more diverse, right? Right? Is this one? So which one will have a high sparsity? %60 rely on this input, right? So production rely heavily on a few specialized source, the input. There's a high sparsity, and compared to the low sparsity, which the input are equally spread, equally weighted, more diverse. Concentrate on one input, that's high sparsity. So if you have this idea how to count the numbers, if Tesla battery technology 50%, highly rely on 50% battery, the other chips, software, materials, less ratio. And we count the sparsity or concentration or specialization. We will use this formula, right? So the weight is 50% square plus the chips 0.25% square, 15%, 10%, and make a summation. So this is for input specialization and the sparsity measurement. Is that correct? Hmm? Question? Okay, then we can compare. For Tesla, we just count it's a 0.345 compared to Apple. Chip 25% input, the weight, theta ji, telecom 20%, design 20, materials 15, this is Apple. So we can come the same idea about the specialization or sparsity. It's like a 0.205. Which firm is highly rely on a dominate input, Tesla or Apple in this case? Huh? Yeah, that's a Tesla because we can see this is higher than 0.2, right? So 3, 4, 5. Okay, so for sparsity check, is Tesla versus Apple's? Why is Tesla knowledge network more sparse? Why? Concept check. Okay, so you guys can answer. input and output. Okay, then we can take a look at your overall answer. Okay, most of you guys answered B because the input shares are more concentrated in a few knowledge source. Yeah, that's consistent with the paper's idea. Okay, then if we continue to discuss this paper, did we skip one slide? The data source. Using CRISP for start return, CompuState for counting variables, and physical network. CompuState have a module related to customer segment data is from there to formulate the network relationship. Knowledge network from pattern view to get the pattern citations, patterns economic value using this paper, and the pattern number USPTO. The other from a French model, and macroeconomic from the Fed, St. Louis Fed. So how do they measure the physical network? I just mentioned if a supply is J, input to customer firm I, and this weight we will count WJI for physical input. For intangible knowledge input, we change the symbol to theta ji. So it's the same logic pattern in sector J, input, output to sector I. But this is intangible, so we use theta ji, and if it is physical, then we use WJI. Then we will have a physical input-output matrix, omega. And the paper used 2-digit sector level rather than like 3 or 4 digit. So here is a paper showing the network. For each one, there is a lot. So using the software to formulate this graphene network size ecosystem. So you can see like numbers. This means the sector's name. You can check the SIC code for each sector. This is not for the numbers. This just count for the sector. You can check which number this sector belongs to. But the larger size means they are the main input. So to the other output, so main input for the knowledge base network. This counts like a centrality, many centrality, the know-how. So this figure is the visual bridge between the model and the empirical factors construction. You can take a look at that for a little while to deeply understand their thoughts. Supply chain. So in empirical model, they count consumption. So using three important independent variable measure knowledge input, change in knowledge sparsity, change in physical sparsity, and the change in concentration level. Control variable and the control for the previous number of consumption. And this formula to the empirical model for the baseline. So the consumption growth is delta, was affected by control variable and macroeconomics and so on. But three important is intangible measurement for knowledge change, sparsity, physical change, sparsity, and the concentration change. Okay, so this is the empirical model the authors provided. So there are some limitations the author also mentioned, but I think they already done a lot, right? So even though it's not 100% perfect, because two-digit numbers like does not actually totally measure the difference between auto firms. Even though these three firms belong to the same digit for two-digit, but they are heterogeneous in other way. They're not identical to each other, but this could not be controlled more in this paper. That's the limitation. And also, the paper mentioned the patent citation may reflect a legal strategy or examiner added citation. It doesn't really count correctly 100% because some of them not really the knowledge transfer. Okay, so I will not using Slido, but take a look at these questions, whether you can answer this. Why do authors use patent citation in this paper? If your answer is A, raise your hand. Your answer is B, raise your hand. C, D, E. Okay, so most of you guys pick B, which is really the idea of the paper. Okay, we move forward to the empirical results. Here is the empirical model we just mentioned. Dependent variable is the growth. Consumption growth. So it's an annual growth of a real personal consumption in non-durable goods and services per capita. This was the academia definition for the paper, the growth. Delta, consumption growth. And the other is a main factor, three main factors, and the control variables for all these macroeconomic data. So this is the result. Here you can see the model along with the results. We can see that high, this is a knowledge sparsity change, right? high knowledge sparsity positively and significantly affect the consumption in model 1, 2, 3, no matter whether the control variable was included. This model 3 is completed model, right? So all positively and significantly affect consumption. And the same thing happened, physical input sparsity. So for knowledge input and for physical input sparsity, and all positively, significantly affect consumption. By contrast, the concentration, high concentration actually reduce the concentration, the third variables. So two variables positively affect the consumption, but concentration, highly concentration, does not. By contrast, it reduces the consumption in this model. So any implication for the model? So how can we explain for this? For the positive delta NSX, more specialized knowledge network will foster higher consumption growth. The same thing happened on more specialized physical network, foster higher consumption growth too. By contrast, if high concentration or highly dominated output by some large sectors, actually lower concentration growth. Okay, so this is the implication of the paper and the model's predictions, consistent with the theoretical model. So not just the consumption, the author next separate the return into different group. You want to test whether more exposed to network risk earned higher return. So whether the risk has been compensated by higher return. So to compute high minus low return and alphas. Okay, so take a look at the results they find. So authors separate the return based on the returns of beta, okay, into three groups: high, medium, and low. If the risk was priced in the model, then high risk should have associated with a higher return, right? It's a high associated with higher return. This is a return. 0.84 is larger than middle beta. 0.69 and larger than low, 0.53, right? So we calculate high minus low should be positive and significantly. So beta sort portfolio, we can see all this model, K-band model, Fama French, 3-factor, 4-factor, and 5-factor, all consistent results. High portfolio, high beta portfolio was compensated with higher return compared with low beta portfolio across all different K-band model. The same thing happened in physical sparsity, all showing being compensated if the beta risk is higher, right? By contrast, the concentration beta have the opposite result. So higher beta sorted portfolio, if with the low beta basis on concentration beta, then investor will require or will obtain the higher return relative to low. And higher beta was compensate with inversely lower return. So all high minus low become negative. So using these methods, we can see that the return on beta sorted portfolio, higher beta portfolio was compensate with higher return. So the market actually price all these variable into the stock price already. And the market also price the concentration beta into the model, the stock price already. So high concentration does not foster stock price, and instead it destroys the stock price. So the author actually think a lot of way to prove something and to design the model consistently. Also, we can see high minus low, these two was positive and have an excess return. So this is a positive premium. By contrast, concentration get a negative premium, which is the paper's prediction in the model, theoretical model. They predict physical and the knowledge sparsity should be compensated with positive premium, while concentration risk should have the opposite sign. Okay, so this is the graphing from the alpha after the standard factors. So it's consistently being pricing. Here is another table that we can focus on. Finally, you have to estimate the market price of the knowledge in the physical network risk, right? So this paper, you can see that more consistent. But which one you think we should start with the beginning? If you ignore these three important factors, I only measure the market 1 and 2, model 3 and model 1, without any invisible knowledge of physical network risk, without any variable included. 1 and 3, without including these three variables. You can see model 1 have a MAE. What does it mean? MAE means absolute pricing error. So the error is the maximum among O. Without including these invisible or physical variables, the market returns have a largest measurement error, pricing error, 13. The full model is in model 5. Include all these three into the model, and the measurement error reduced to 4.07. significantly improve. So that means these three factors really work to explain the stock return. We cannot ignore them. If we ignore them, then we will have a measurement error, which is the maximum. If we include them and include the others, we will have the smaller measurement error, and the story always consistent with the theoretical prediction. Positive, positive, and negative. And there is another number that I need to mention is p-value. The p-value here is a JT statistic that asks whether the model errors are not significantly statistically too large. Also, all this reject. But model 5 say, don't reject, so accept. So if this is too large to be acceptable, it's not too large to be acceptable. The non-hypothesis is that too large to be accessible from this model, and we can see the p-value is 0.83, not rejected. So in this case, not rejected means the pricing error are not too large to be acceptable. So this becomes inversely a good result compared to the others. Okay, so this is 4 minus 5. Okay, so we can see becomes 0.83. If you don't really understand this JT statistic, you can only focus on the measurement errors to think that when we include all three into the model, the errors fall a lot, which means that network factors really work to explain the market model. So this is the result from the previous table, and the knowledge network risk enter the pricing model. So a lot of contribution and a lot of things that you can learn. For MBA takeaway, first, if academic contribution, we will say like these words. They add the intangible asset into the pricing model. But what we can learn is intangible linkage can be systemic risk, not only a competitive advantage, because we find that the low, median, and high, each with a beta, right? And actually is significantly compensated by actual return. So this is a systemic risk. And we also learned that pattern data can reveal hidden industrial dependency. So there's an input-output flow which was not observed in traditional supply chain model. But these modern firms, supply chain model, including invisible pattern citation network, which should be counted in the pricing model. And firm exposed to innovation network shock may require risk premium, right? So we're already pricing that positive, and two, well, gain a risk premium. And finally, the manager should map both physical and knowledge supply chain. Should map this and pricing this invisible input into the market model. So stock market should price both. So this we can learn from this paper. However, some contribution, we can go back to the contribution. We have 2 page skip, right? So we go back to the so the paper fits. Why I come back to here? Because next week, we will focus on network centrality and topology. This paper actually is the beginning of the next session, talking about the network betweenness, centrality, and many other measurements. So most physical supply chain model focus on tangible input and product output, all tangible. Last paper focus on how IP and knowledge move across sectors, and this paper fill this gap. So by literature review, this paper add concentration paper and linked to the economic link and linked into network centrality paper and linking to distance to customers, competition, trade credit chain, international trade network paper, and also this paper related to uncertainty, volatility transmitted paper, along with supply chain. So this paper's gap to fill all this intangible input, pattern, algorithm design, know-how, and into the model. So knowledge can flow across sectors even without direct physical trade. This is quite important. So the structure of this knowledge flow becomes systemic asset pricing risk. The answer was yes. So the model can apply to similar sectors and become a systemic asset pricing risk. And the next page is the last one. The paper's contribution, we can see traditional innovation views. View as technology as an aggregate shock or firm levels characteristic. But this paper is saying knowledge input output network, inflow, outflow across sectors can be an asset pricing model and have some implication in there. So knowledge network risk help explain risk premiums and stock return. So theoretically, it contributes the model, but empirically, it actually can be extended more. We can measure the knowledge network sparsity, physical network sparsity, and sector concentration, and using patterns citations, patterns value to construct the knowledge flows across sectors. So all this are significantly and consistently using different models. So this is the bottom line that we can learn. IP is not only a source of innovation advantage. On this paper, we can see knowledge network become a systemic risk factors already priced by investors. Okay, so very consistent, very condensed, right, this paper. Even though some theoretical model may be more technical, too technical for us to learn. However, the intuition and the idea are quite practical. Because this author have another, I think it's a Journal of Finance or Journal of Financial Economics, top tier finance journal. Maybe it's Journal of Finance. Have another paper already published in Journal of Finance. They count the pollution premium. They're already done and being accepted and cited by the other paper. They count the pollution premium using very similar methodology. And this paper, because that's a successful case, and the authors switched this issue to count the risk premium of the knowledge network risk. So apply the same idea but into the different issues and count the different angle, which is really interesting. You can check the authors, Professor Xu, the first author. He's a very good researcher here. In National Tsinghua University. Okay. So you can check his name and to read the paper if you are interested in the pollution premium. And this is the knowledge premium, knowledge network premium. Questions? Any questions? Any part need to enhance again? Huh? Theta JI, WJI, and how to count these measures and whether, okay, we can compare to example to Apple and Tesla. We have idea check, and we have the measurement and the results, right? And how the paper's doing and how we explaining and to apply it to your research in the future. And about the data, about the model, about the results. Very consistent. Yeah, very consistent. So far, I think the experienced researchers doing the design very concerned. Okay, so I think this table 4 is quite important, being the last conclusion that we can apply it to. Okay, any questions so far? Okay, if no further questions, then our discussion will end here. Okay. Thank you for your presentation and participation in the class. I will see you next week.